In this video, we will demonstrate how to use the Differential Auxiliaries proof rule in KeYmaera. Differential auxiliaries, sometimes referred to as differential ghosts, are useful when we have a differential equation which is not solvable in real arithmetic, or which is computationally intractable. In a previous video, we looked at differential invariance for dealing with these tricky differential equations, and in fact, differential invariance and differential auxiliaries go hand in hand. In some cases, there isn't a strong enough differential invariant to prove the property given the variables available in the system. In these cases, we can rewrite the property we want to prove using an auxiliary variable, and then allow the auxiliary variable to evolve in a way that we choose. Let's look at an example. Initially, we have that x is greater than 0, and then we allow x to evolve along the differential equation x prime equal negative x. And finally, we want to show that x is greater than 0. The solution to this differential equation is e to the minus t. We know that e to the minus t has an asymptote at 0, so we know that this property is going to be true. However, since x gets closer and closer to 0 as it evolves, we know that this might be a little tricky to prove without plugging in the solution. So instead of trying to prove that x is greater than 0, we're actually going to come up with a new property that relies on an additional variable, our auxiliary variable. In this case, the property we've come up with is that x greater than 0 is equivalent to saying there exists a y such that x times y squared is equal to 1. We know that the only way that this property can be true is if, in fact, x is greater than 0. Now we're allowed to add a derivative for y into our differential equation, and we choose y prime equal to y over 2. This choice is not arbitrary, and you'll see that later in the proof. We'll also need an additional side condition that this derivative is well defined. This means that the evolution can't just stop in the middle because y is no longer able to evolve past a certain point. As you can see, we've replaced the initial condition and the final property that we're trying to prove with our new property that includes the variable y. Now that we have the property in this form from the differential auxiliary rule, it's in a perfect state to now apply the differential invariant. As you can see, we take the syntactic derivative of x times y squared equal 1, and we get x prime times y squared plus x times 2 times y prime equals 0. Now we substitute in the values for x prime and y prime. Now it's clear why we chose y prime to be y over 2, because now this syntactic derivative of our property cancels out and is exactly equal to 0. So we're able to close the proof. If you want to visualize what's going on here in terms of the actual solutions to these differential equations, you can think of y prime in terms of its solution. So the solution to y prime equal y over 2 is just e to the 1/2 t. So y squared is just e to the t. Remember that the solution to x prime equals minus x is just e to the minus t. So now our property becomes e to the t times e to the minus t equals 1. Okay, now that I've shown you how to do this proof by hand, let's see if we can figure out how to implement it in KeYmaera. So we've written this same property in a .key file, where we start with x greater than 0, and we show that if we evolve with x prime equal to minus x, then x will always remain greater than 0. We've loaded this property into the Theorem Prover, and the first thing that we want to do is hover over the box modality. Clicking on that, we have a menu that pops up showing a variety of rules that we could apply. The rule that we're looking at today is the differential auxiliary rule. This rule requires several instantiations. First, we have to choose a name for our auxiliary variable. So far we've been using y. Next, we have to define how our auxiliary variable is going to evolve. In order for KeYmaera to ensure that the differential equation is well defined, we actually limit the evolution of y to be linear. So in this box we input our linear coefficient, which we recall as 1/2. And in the next box we can add a constant. In this case we had y prime equal 1/2 y, and we didn't add a constant, so we'll just make that 0. Next, we'll fill in the box with the formula that we want to be equivalent to what we're trying to prove, except in this box we'll leave off the exists y. In this case, it's x times y squared equals 1. We then scroll down to the final option. We want to use the basic definition of the differential auxiliary rule, so we can simply use the auxiliary variable y here, and then click Apply. As you can see, the KeYmaera prover generates 4 different branches. There are more branches than we saw in the proof that was done by hand, because we additionally have to check that the property was initially valid and that the differential equation is well defined. These steps are a little obvious, and so in a hand proof we might skip them, but KeYmaera won't let us get away with that. So first we show that the property is initially valid, and this is trivial. The next property that we have to prove is that x greater than 0 is indeed equivalent to the property that there exists a y such that x times y squared equals 1. KeYmaera again can handle this automatically. Next, we have to show that the differential equation is well defined. In this case, the only thing we need to show is that the denominator is not equal to 0. So where we had y prime equal 1/2 times y, we had 2 in the denominator. If we had divided by 0, then this differential equation would not be well defined. This property is again obvious, and KeYmaera handles it easily. And finally, we're at the last and most difficult branch of this proof. This is the part of the proof where we show that adding in that differential auxiliary variable makes it possible for us to apply the differential invariant proof rule. So let's do this by hand. Next, we get rid of these for alls by doing a substitution with a new variable. Now we can apply the differential invariant rule using x times y squared equal 1 as our differential invariant. You can see that the differential invariant holds initially by design. And now we recognize the syntactic derivative of the differential invariant with x prime equal minus x plugged in and y prime equal 1/2 y plugged in. And at this point, it's just a real arithmetic problem, and so KeYmaera is able to close the proof. Thanks for watching this video on how to apply the differential auxiliary proof rule in KeYmaera. This video is part of a series of tutorials on the KeYmaera Theorem Prover. To learn more about KeYmaera or to download the tool, visit keymera.com.